everyone, this is our fifth video about the physics principles that can be applied in the construction of a tube balloon. Okay, what we're dealing with in this video is this idea of end correction. So this is our second model. So this is a model which is used to calculate the particular frequency that is created in a pipe of some particular length, but special consideration is put in place in order to get a more accurate reading about that length and the frequency related to that particular length pipe. Okay, after this we should also be able to derive the particular equation for the closed pipe with end correction. Okay, so normally when we're talking about the creation of a standing wave in a closed pipe, it is understood that as that wave travels along the pipe, the compression phase, once it reaches the closed end, it will hit the closed end and it will get reflected back to the open end. When it gets to the open end, that compression phase, which has been reflected back, dissipates into the atmosphere, and what happens is a ricochet effect happens, and that refraction gets thrown back down towards the closed end, and again that continues on, so that gets reflected back as a refraction. It goes to the open end, but in this instance the extremely low pressure region, which is the refraction, interacts with the atmosphere, and the atmosphere races into that refraction pocket, and it creates another compression wave, and the cycle continues on. Ultimately what would happen is you get a destructive interference node that's created near the end, and a antinode towards the open end. Now this is all good and swell, but what actually happens is this doesn't occur in the boundary that we have talked about in the first model. What happens is that exchange between the compression phase being dissipated into the atmosphere really occurs at some distance away from that boundary line, and that distance is given by this variable E, some particular length away from the boundary of the pipe. It's given by this variable E, and that variable E is called the end correction. So what's happening is it's almost like you're summing the actual length of the pipe plus that end correction to get a more accurate value for the frequency of that pipe. Now we can just continue on from the previous expression that we derived for the relationship between wavelength and the length of the pipe in our first model, which is a quarter of the wavelength that can be formed in that pipe, and the particular harmonic value presented as a fraction multiplied by the particular wavelength found in that pipe gives you the length. Now all we have to do to adjust this expression is at this end correction value, right? This end correction E, we don't really have to denote as a particular value. We just know that it's there. We know that the length of the pipe plus this distance that is away from the pipe must be considered in this new expression. So that's all we've done here. We've added that E variable in there. Now the unique thing about this end correction variable is that it's got a relationship. It's got a relationship with that of the diameter of the of the particular pipe. So if that pipe is, say, it's got some kind of diameter of 0.0025 meters, well, then you multiply that by this factor of 0.486, and that should give you an estimate or some kind of value for that end correction that occurs, which makes sense. That space where the pressure waves dissipate over the atmosphere is related to the diameter of the hole of the pipe. Now, this is an experimental value, and that can vary depending on the diameter of the pipe, but the general value is given by that. Okay, so looking at this expression again, so again we got n is equal to the particular harmonic that is occurring in that closed pipe. Remember, these are odd numbers, so they go up in odd numbers. So we got number 1, third harmonic. You can also have a fifth harmonic. You can have a seventh harmonic, and you can also have a ninth harmonic. Whatever odd number harmonic you can create in that closed pipe. The number 4 is a constant. The wavelength is something that can be measured, and it's usually related to the length of the pipe. Now, the only variable that comes up here that's different is this end correction value, again, which can be determined by the diameter of the pipe, or it can be algebraically or mathematically determined. So let's have a go at calculating or deriving the expression for the frequency of a closed pipe with the end correction. Okay, so our first equation is this. The particular odd harmonic for a closed pipe divided by 4 multiplied by its particular wavelength is equal to the length of the pipe plus that constant E, which is that end correction in that pipe. Now again, the emphasis is always solving for wavelength. So that's our first equation. And our second equation is frequency is equal to the speed of sound divided by the wavelength. Let's get equation 2. So we rearrange this for wavelengths. We get wavelength is equal to 4 times the length plus end correction divided by the n harmonic. And what we're going to do is substitute this value in there, and then we'll simplify for frequency. So let's do that. Frequency is equal to the speed of sound divided by 4 times the length plus the end correction divided by the nth harmonic. Remember, that 4 gets distributed over each one of those variables there. As we simplify, we end up getting something similar to what we had before. Okay, L plus E.